My talk comprises of these two works here, one with Marcelo that just presented here, and another more recent paper with Rafael Wagner, Cristiano Duarte, Barbara Amaral, and Marcelo again. I think everybody is here, so maybe in the discussion we can talk to everybody in this work. So let me start posing the problem, okay? So my first claim is that contextuality is a non-classical feature, right? Then my second claim is that our everyday experience as observers is classical. And finally, that quantum theory is contextual, right? So when we put all those three things together, if we aim to have a classical limit of quantum theory explaining our everyday experience, then it must be the case that this classical limit must kill quantum contextuality so that it can be regarded as a good classical limit, right? So the main question of this talk is, does contextuality disappear under classical limits? So this is the main question that I want to address. And just to give you an outline of my presentation, the first part, we will analyze one specific class of non-contextuality inequalities, where we substitute the usual one observer setup by a sequential observer setup. But you're not going to look into details of it. We are just going to try to understand what is the message in terms of emergence of non-contextuality here. And one of the messages is look into Darwinism, okay? So this might be a classical limit capable of killing contextuality. So this will be the subject of my second part, and spoiler alert, no contextuality does emerge under quantum Darwinism. Okay, so let's start the first part of my talk. So to do this, we need first to set our ground. So I have to talk to you about n-cycle inequalities. And actually, I am very happy that Etibar and Daphne already told us about cyclic systems. So actually, Etibar told us everything about cyclic systems. So actually, I just want to wrap up quite quickly here, okay? So first of all, I'm always assuming that the non-disturbance principle is exactly obeyed here. So there is no disturbance, okay? And for cyclic systems, we have some n measurements here. And what is important is the compatibility structure, right? So the context are A0 is compatible with A1, A1 with A2, and so on until we close the cycle, right? So we are not even going to look into all n-cycle scenarios, but only those with an odd number of measurements, because those you cannot split quite naturally between two parties, okay? So nice, we have n-cycle scenarios with odd n, and now we are going to consider that our measurements are dichotomic, okay? So in a joint measurement, right, of a context, we have 4 possible outcomes, okay? And one of the inequalities defining the facet of the non-contextual polytope is this one here, okay? And the others are related to this one through relabelings, right? But well, they are different, and I want to focus on this one. Now, if we make an extra assumption that instead of 4 outcomes, actually one of them is always forbidden, okay? It never occurs. So essentially, our joint measurement has only 3 outcomes. In this extra assumption we call exclusiveness, we actually can come from this inequality to 2 different inequalities here. Okay, and these are the inequalities that I'm going to use, right? With a slightly lighter notation, okay? So all of these here, +1 to both I and I + 1 measurements, I will call outcome BI, and -1 outcome for the ith measurement, I will call it AI, okay? So these are the inequalities that I'm going to use for the n cycle, okay? So nice, we have these inequalities here, and now we can ask, well, how can we test these inequalities, right? So, well, looking at them and considering what you're talking about, at least 3 protocols come up to our minds, right? So the first one, well, you measure a context, you might get one of the 3 outcomes, and then you can calculate either this value or this value and see if you got a violation or not, right? Or you can actually coarse grain these measurements into a measurement which is AI or not AI, and only calculate this guy here. Or you can do another coarse graining and obtain BI or not BI, okay? And then calculate this guy here, okay? And then you can see if you get a violation or not. These protocols are usually equivalent, okay? So in the usual setting. And finally, I want to talk to you also about quantum realizations for the n-cycle inequalities, okay? So the best quantum realization can already be seen in a Hilbert space of dimension 3, where the observers are written in this way: identity minus 2 times a projection, right? So these vectors here defining the projection, they must abide by this orthogonality relation here, okay? And this is necessary so that these guys here really obey our constraints on compatibility, right, of the cycle scenario. However, in this quantum realization, this implies that they obey also exclusivity, okay? So if you are actually performing this quantum realization, then exclusivity is naturally obeyed. So if you violate one of the inequalities, you're really violating non-contextuality, okay? So nice. So now how would you test these inequalities usually? Well, you have one observer, and this observer makes measurements on a system recently prepared, throw it in the garbage after the measurement, and then repeat this process until sufficient statistics is gathered, right? So now what we want to do is, instead of throwing the system in the garbage, the first observer passes the system on to the second observer, and so on and so forth, okay? And each of the observers here will be implementing one of the protocols for the best quantum realization, right? So this is interesting from the point of view of quantum information protocol. It's a specific protocol, okay? And there might, be interesting without even talking about emergence of non-contextuality. However, what I want to do here is to focus on the message that this protocol gives us in terms of emergence of non-contextuality in open quantum systems. So let me show you a typical result that we obtain. So let's focus first in this left plot here, okay? So this shows to us the value of this sum of probabilities here obtained by the first observer, the second, and so on, okay? And the second plot shows us what is the value obtained by the first observer, the second, and so on, depending on the protocols, okay? Every dot in the gray area means that there is no witnessing of violation. In the white area, there is some violation there, okay? So what can we see? So let's first look into quite big numbers of observers. What you can see is that the values quite quickly approach this asymptotic limit here, which you prove to be n over 3. So in this case here, 3, right? And this number is in the gray area, so there is no violation, okay? So the first thing. And the second thing is that it's not true that asymptotically there is no violation, but for a large number of observers, there is a violation. It's actually the opposite. So for instance, in the left plot here, only the first observer sees any violation. And here, for the third protocol, BI or not BI, there is a little bit of observers that can see it, but quite quickly violation disappears and no observer can see any violation anymore. So these are the two main aspects that I want to focus now, okay? And well, it's important to say to you that I showed you the 9-cycle results, but similar results can be attained for any n, okay? Any value of n. And this means that for any value of n, I can always find a large enough k in which violation disappears, right? So now let's interpret these results in terms of a classical limit, okay? And to do that, we are going to look into our sequential setup, but we are going to interpret these observers here, the sequential observers, as an environment. And please note that we're not talking about an environment that is like in the decoherence paradigm, where you have a monolithic environment that you trace out in the end. Actually, we have an environment split into several subsystems, right? And what is important is what these subsystems have to say about the central system here, okay? And actually, this interpretation as an environment can be recast in terms of interactions. So a state is prepared, and then it undergoes one interaction with one subsystem of the environment, okay? Then it becomes a post-interaction state instead of a post-measurement state. And then it undergoes another interaction with another subsystem of the environment and so on, okay? And then through this interaction, some information about the central system can pass to the environment. So once you look at it for the first time, it might be quite artificial way of considering a system-environment interaction, but it's actually a very powerful and useful approach to open quantum systems, which is called a collisional model approach, okay? However, I must say to you that, well, our results consider projective ideal measurements for the observers, okay? Which means that here, each of these interactions are strong, which takes actually us apart from the collisional usual way of thinking of collisional models, okay? However, the interpretation a la collisional models still hold. So with this interpretation in mind, what do these results tell us? Well, first, if independent observers learning about the system through independent portions of the environment, and they are learning about the system in this way, and then you can ask them, can you witness contextuality or not? A vast majority will say no. Okay, there might be a case where one or another yes comes up, but most of them, the vast majority will say no, which means that dynamics makes contextuality disappear in this case, right? So what is the take-home message? Well, in this very idealized and very special environment, contextuality disappears. So since this is a very special kind of environment, our question in more generic terms is still open, right? So does non-contextuality emerge in more generic classical limits? So this we want to tackle in a few minutes, okay? However, to tackle this question, this example also gives us a hint. And the hint is you should look into classical limits taking place in this kind of environments where you have several subsystems, and you should look into the information that these subsystems have about the central system. And why is that? Well, because it's an environment really designed to test contextuality, and it fails. Okay, so essentially this suggestion here is, well, if you are suspicious that someone could kill contextuality, go investigate quantum Darwinism. So let's do that now in the second part of the talk. So to do that, I have again to set our ground. And so first I have to tell you what quantum Darwinism is, and in particular, which approach I'm using, which is due to Brandão, Piani, and Horodecki in this reference, a very nice paper here. And I will be calling from now on Brandão, Piani, and Horodecki BPH, okay? So what is quantum Darwinism? So the essence of quantum Darwinism here can be depicted from this picture here, okay? So we see that a person is reading a book. And why does she see the book? Okay, well, because a bunch of photons is interacting with the book, and then a small portion of it is going to this person's eye. If there are another person here, this person would also see the book by the same mechanism here, right? So how can we describe this in a system environment interaction? Well, we have a central system A here. This system interacts with the environment, and this interaction makes some information about the central system leak into the environment. Okay, then we are not going to look into the system or the whole environment, but actually into just a small portion of it. So this idea that a small portion of the environment can work as an information channel between the central system and an observer is called an environment as a witness dynamics. Okay. So now, on top of the environment as a witness dynamics, one process called quantum Darwinism may take place, and its goal is to explain why different observers having access to even smaller portions of the environment, they will agree on what they infer about the central system, okay? So now let us formalize this idea a little bit. And first, this big dynamics is described by a CPTP map, which I call phi, and then we are going to trace out everything but one small portion. And this small portion I will call BST, where T here stands for the number of individual subsystems. So here, for instance, T equals to 3, okay? Then the dynamics that you're interested in is this effective dynamics described by the CPTP map phi BST, okay? And what is phi BST? Well, it's just a big dynamics and tracing out everything but the subset given by BST. And we are calling this dynamics the environment as a witness dynamics, okay? So now what BPH tells us is that, well, they have a very strong result telling us that the phi BST dynamics, the environment as a witness dynamics, where there is a big dynamics followed by tracing out everything but a few subsystems of the environment, is approximately given by a measure and prepare map. Okay, and what is a measure and prepare map? Well, the central system undergoes a measurement, and depending upon the outcome of this measurement, a system of the portion of the environment is prepared. Okay, mathematically, this can be described in the following way. So consider that we are looking into a portion of the environment that is really small compared to the whole environment. Okay, then for most choices of portions of the environment that we are going to look at, the phi BST is essentially or approximately a measure and prepare map. Okay, and the remarkable feature here is that this POVM defined by the measure and prepare map is independent of which part of the environment that you're looking at. Okay, I have also to say that nothing is said about these states here. So these states may be any state on the Hilbert space of BST. Okay, And that's it. And the remarkable message that this theorem tells us is that environment as a witness alone already leads us to some notion of emergence of objectivity, okay? Which is called objectivity of observables. So why is that? Well, again, because the observable monitored or selected by the environment is independent of which portion of the environment that you're looking at, okay? So now, from now on, I will consider some assumptions, in particular that the environment is not big, but actually infinite. And this allows us to exchange the approximation by an equality. So our phi BST map is now exactly given by the measure and prepare map, okay? Okay, so this is nice. We already have some notion of emergence of objectivity of quantum systems, but this is not enough yet, because what quantum Darwinism wants is to say why this Bob here, and this Bob here agree on the outcome that they see, agree on every inference that they make about the central system. Okay, so let's see how this can happen. Okay, so for that, we have to take each Bob's perspectives. Okay, so just trace out everything in BST that is not BJ, where J goes through all the Bobs, and then the state that they receive is this one here. Okay, and remember that we haven't included any restrictions on the sigma case here. However, to have a proper quantum Darwinism process, this information about the label K must be well encoded in this encoding state sigma K. Okay, so now we are going to say that the quantum Darwinism process happens if the sigma K encode well enough the labels. Okay, which is essentially the same thing as saying that these guys here, these states are sufficiently distinguishable. Okay, so this is nice, but how can we quantify this? Okay, and this is how we can do that. So let's call this probability distribution here P2 decay, which of course depends on the state of the central system. Okay, but now we can see that trying to guess which of the label Ks were prepared by receiving this affected state is essentially an instance of a minimum error state discrimination task, okay, where state sigma Ks are drawn according to a priori distribution P2 here, and the task of Bob is to try to guess which label was there. Okay, so one figure of merit to quantify how successful Bob can be is the probability of guessing, which depend on both the sigma case and the P2 decay. Okay, so if the sigma case encode really well the labels, so they are really distinguishable, then the p-guess is really high. Okay, so this is how we can quantify how well these states here encode this information. So with this p-guess in mind, we can finally define a quantum Darwinism process. So we have an environment as a witness dynamics and the partial traces to each of the Bobs. So now a QD eta, QD for quantum Darwinism, so a QD eta process occurs if for all of the Bobs, the p-guess is at least eta. Okay, so if eta is high enough, then the p-guess is high enough, which means that the states arriving to Bob encode really well the information selected by the environment. Okay, and then this is just again to remind that quantum Darwinism requires that the information is really well encoded in the environment. Okay, so now we have another very important result from BPH, which is that environment as a witness dynamics plus good enough encoding, okay, which are calling here QD eta with sufficiently high eta, implies that all Bobs are likely to agree on the outcome they see. Okay, so the Bobs here essentially see the same thing. Okay, so now we can say that QD eta with sufficiently high eta implies also objectivity of outcomes. The Bobs see not only the same measurement being made on the system, but the same outcome as well. Okay, so this is really nice because, well, the environment as a witness dynamics explains, or at least describes our generic experience as human observers, right? And here, no assumptions on the interactions are made. Any CPTP map will do. So this is really striking. However, there is a small drawback that the monitored observable selected by the environment can be anything. There is no a priori restriction on this guy. So E2 decay can actually be an informationally complete POVM. So this makes our question even more subtle because, okay, you are finding some sort of objectivity or agreement between observers, but why should we call this agreement classical if essentially all information about a quantum system can be there, right? So this is what I want to answer now. And to do that, we have to take Specken's notion of contextuality. Okay, and well, when doing this, we actually have to be very careful to analyze what are the equivalence classes for the different procedures. Okay, and we do so in our paper, and if we want, we can discuss this further afterwards. But what's important is that taking Specken's notion of contextuality, we can prove this result. Okay, so if you have an environment as a witness dynamics and the reduced dynamics for each bob, then for those bobs in which the encoding states are finally independent, then there exists a non-contextual model for the statistics, okay, for these bobs. So essentially, what this result is telling us is that the EWT dynamics plus a fine independence of the encoding states imply non-contextuality. So this is nice. We get some notion of non-contextuality out of interaction of quantum systems. However, this condition of fine independence is not really operational, right? So to fix that, we have a second result, which is the following. We can prove that there is a bound p hat here, which depends only on the monitored observable by the environment or selected observable, such that if the p gas for one bob bj is higher than this bound for every initial state of the central system, then the sigma case must be affinely independent. Okay, so let's recall that the usual situation that some state is arriving to Bob with some information about the central system can be recast into instances of minimum error state discrimination. We can actually see this lemma as interesting, even if you don't care about quantum Darwinism nor contextuality, right? And what does this lemma tells us? Well, if p gas is high enough, then your sigma case encoding states must be finally independent. Okay, so now let's put lemma 1 and 2 together, and we obtain our main result, which is that if a process of QD eta occurs with eta higher than our bound, then every Bob can construct a non-contextual ontological model for their statistics. Okay, so another way to say this is that quantum Darwinism with sufficiently high eta implies non-contextuality for every Bob. Okay, so this is the main message of this talk and the main result I wanted to tell you. But it will also be interesting to tell you a few more bits about this work, which is the following. As you saw, we're assuming this equality here, which holds in an infinite environment. However, if we consider a finite environment relaxation, then we have only an approximation here. Then we could not prove emergence of non-contextuality per se, but we can prove that one quantifier of contextuality based on the L1 norm is constrained, is upper bounded by this value epsilon here. And under usual situations of environment system interactions, this bound is really small, right? So we don't get non-contextuality, we don't kill contextuality, but we constrain it a lot. So to conclude, we show that non-contextuality generically emerges out of quantum Darwinism when the environment is infinite. And actually, this is even a bit weaker because Darwinism can fail, but non-contextuality is still emerge as long as we have a fine independence of the encoding states, okay? And I think this is interesting if someone likes Darwinism and never heard about contextuality, because it gives an argument to say why the word emerging out of quantum Darwinism, and mainly in the BPH approach, can be called classical, at least from the point of view of contextuality, right? And finally, if we consider finite environments, we prove that contextuality is really constrained, okay? And then actually, finally now, we can show a bound on minimum error state discrimination tasks that tells you, well, if your p gas is high enough, you gain some geometrical knowledge about the coding states, namely that they form a simplex, right? They are vertices of a simplex in the state space. And then we have some perspectives. So for instance, do other classical limits also kill contextuality or not? And well, we can also take all of this approach and instead of considering generic interaction, we can actually consider some specific ones and see if no Markovianity can protect a little bit contextuality or not, and so on, okay? And in this spirit of specific interactions, we can actually go back to our multiple observers and analyze limits with weak interactions instead of strong to see if we can also protect contextuality. So that's all I had to say. Thank you very much.